this is kind of unprecedented situations because of coronavirus thing. So we are trying many things new. So as you remember, so by the time we started this course and semesters, we didn't expect this. So the course was newly designed almost from scratch. So our TAs did a lot of work on this. Also, our professors spent a lot of time on this, being adjusted to a new class format. And also, most of all, students, you guys have worked hard. 네. 네, 지금 좀 피드백이 돼서 제가 그냥 목소리를 조금 더 크게 하면 될까요? 괜찮으실까요? 네. 네. So sorry about that. So thanks for your participation and cooperations under these very difficult situations. And the brief schedule today is we are going to have a presentation session from now to until around noon, maybe a little bit more because we have some delay right now. And then we have a short lunch break, and we are going to have a demo session from 1 p.m. So you guys submitted the code yesterday by 1 p.m. and also you had TA sessions for submission. And our TA actually they stayed up the whole night and running your code. So we are going to show the best clips from your code, and you are going to see that and hopefully broadcast through YouTube from 1 p.m. And that's what we are planning. So from now we are going to start the presentations. Each team, we give 10 minutes for presentation and including interaction. So let's see how we should make things a little bit more flexible because of this kind of issue. So who is the first team? We have 8 teams here. Who's the first presenter?
Good morning, this is Team D, Chiros, and my name is Jung Han, who will present our final design review today. This is our table of contents. I'll define the problem again, and I'll show you the demo video, how we did on the project, and I will explain the hardware design that we did in the following order, and I will explain the software design we did. And let's look at the problem first. In this project, we are given to pass through this entrance zone and collect all the 3 blue balls in the harvesting map and dump them into the goal area. And let's see the demo video that we created. First, it proceeded the line tracing in the entrance zone, overcoming the slope and the bumps. And when it finishes the line tracing, it starts the ball harvesting. Yeah. So let's look at the hardware design that we did for this project. And this is Cheetos, our robot, and we painted it into orange color to look like it's a Cheetos. And this is our specification for the hardware. Total mass is about 5.6 kilogram, and center of mass is well placed inside of the body center. And the body inertia can be visualized by the gazebo like this. And we used various sensors here. First, IM sensor we used to measure the vertical acceleration for the slope detection in the entrance zone. And we used total 4 webcams in the project. First webcam we used to push the balls in the goal area, which is placed at the backside of the robot. And for the second webcam, we used it to proceed the line tracing. And the third webcam, we used it to collect and store the ball. And fourth webcam here, which is the most important one, it is used to detect the balls in the harvesting zone and calculate the coordinates of each ball. And the LiDAR, which is placed at the top of the robot, we used it to map the arena and bypass the obstacles. For the ball collecting algorithm, we decided to use 3 ball at once algorithm because we think that it is more time efficient. And in the ball collecting structure, there are several functions. First one is dumping here. We push the balls by using this kind of structure at the end of the project. And the ball collecting part, which is the place where the balls are placed inside the robot. And the wheel guard, this protects the wheels from the red balls and the obstacles from colliding with the wheels. And the lower chamfer, we cut out this lower portion because we continuously detected it collide with the slope in the entrance zone. And for the steering system, we did some various simulations on many structures, and we decided to go for a spherical caster wheels system. It showed the most smooth steering concept, but its disadvantage is that it is difficult to design in reality. By using the two-wheel driven and spherical caster wheel system, we can use velocity differential drive system to rotate at the fixed position here. And for the detailed view of the caster wheel, we set offset of 30° from joint rotating axis here to reduce stress and make sure it does not hinder the rotating motion. As you can see here, if the joint axis and the rotating axis are aligned like this, it would hinder the rotating motion. So this is our safety guard. This is our suspension system. We wanted to use double wishbone suspension system, but we found out that Gazebo does not support closed loop structure, which hardware file does not spawn in the Gazebo. So we decided to replace it with simple shock spring damper system, which is designed as a prismatic joint with PID position controller. And this is the vibration control result at the bumps in the entrance zone. And let's look at the software design. In the entrance zone, we need to do line tracing. So we receive image from the camera and distinguish the black line and convert this black line into white pixels, and everything else in the background is black pixels. We proceed the edge detection using Kenny algorithm and calculate the offset continuously while we are doing the line tracing. It scans all the horizontal rows of pixels and detects the center line, as you can see here, blue line. And it continuously calculates the offset from the center line from the lane on the ground with respect to this center line in the image. So it could follow the line with PID control. In the entrance zone, there are 3 exceptional cases. First is bump. As you can see here, there is no white line on the bump. So this is characteristic of the bump situation. So white pixel to a transition from white pixel to non-white pixel happens at the bump. So we count these numbers, and if it is over 1, we conclude that robot is on the bumps. So we modify the motor input. And for the slope condition, when the robot enters the slope, it gives negative y angular velocity, and it gives positive y angular velocity when it escapes the slope. So we detect this by using IMU sensor here and use it to modify the motor input. And the endpoint of the entrance zone can be characterized by this. As you can see, there's no line condition continuously happens after the line tracing. So if this condition is over our threshold set, we start the ball harvesting. When it enters the ball harvesting zone, it uses LiDAR and particle filter to calculate the absolute robot position in the map. And the camera, LPCV, proceeds the image processing and gives the ball position or the ball coordinates in the map. And this simultaneously updates the red ball and obstacle positions and locates the robot position in the map, as you can see. When it enters the zone, it constructs this kind of map and starts rotating. When it detects 2 blue balls, it starts to align and approaching. The reason why we set it as 2, not 3, is that there is always possibility that 1 blue ball could be hide behind the obstacles, or it is out of our camera range. So after the 2 blue balls are detected, we calculate the distance to each ball and select the smaller distance value one and decide to approach this ball, which has smaller distance. After the target ball is set, we use PID controller input for the rotational motion and proportional control input for the linear motion. As you can see here, x1 represents this left and right coordinates respect to the robot. So our goal is to make this x and y value to 0. After we combine this linear input and rotational input to the motor input, we put saturation function on the motor input to prevent too large velocity input. So as you can see here, robot approaches like this. And there are 4 exceptional cases in the ball harvesting zone. First one is ball stock situation. When the robot approaches the blue ball in wrong alignment, it moves backward and realign with the ball. And the red ball front condition, which detects the red ball in front, it moves backward and bypasses the red ball. And for the obstacle front condition, if there is a pole like this is in front of the robot, it filters out the scan data. As you can see here, this white point is point cloud data filtered by the point cloud library, and it bypasses the obstacle. For the wall condition, it is similar to the obstacle condition. It detects the wall and escapes from the wall to freely rotate. After the alignment and approaching is done, the view is like this. If the upper cam detects the blue ball and lower cam detects the blue ball, there is a conversion from the upper cam to lower cam. So if the blue ball disappears from the upper cam and appears in the lower cam, we use lower cam data to collect the balls like this. This is the threshold value that we set. If the ball is above 0.170 meters, the robot keeps go forward to collect the ball safely. And if the 3 blue balls are all collected, the lower cam view is like this. If this condition continues over and over, we decided that robot collected all the 3 blue balls successfully, so we start moving to the green ball position. And here, as we have the constructed map and the absolute green ball position, we use our robot current position and the absolute green ball position to approach the green ball. As you can see here, it is about 8 meters far from the starting position and 1.5 meters above the starting position. And this is the final step of our robot. It pushes 1 ball by approaching and turns backward to push remaining balls to the goals. Thank you for listening, and if you have a question, feel free to ask.
네, 한국말씀. 잘 봤습니다. 처음부터 너무 강력한 팀을 본 것 같은데요. 상당히 잘 된 것 같고요. 질문은 그 안티 바이브레이션 브레이크가 이제 빠르게 넘어갔는데요. 된 건가요?
저희가 그 포지션 인풋으로 이제 PD 컨트롤을 통해서 좀 조정을 해보려고 했는데 생각보다 결과가 좋지가 않아서 일단은 피크 포지션에서 디크리즈가 일어나서 없는 것보다는 낫겠다 싶어서 넣어놨는데 사실 저희도 이 성능에 대해서 만족은 하지 못한 상황이라서 네, 그렇게 말씀드리고 싶습니다.
바이브레이션 컨트롤이라는 게 그 PD 개인값 조절했다는 거죠?
네, 그 포지션 컨트롤러로 쓰인 그 이번에 프리스매틱 조인트에 포지션 컨트롤을 달아서 이제 거기에서 PD 게인을 좀 조절해서 바이브레이션 잡아보려고 했으나 생각보다 이게 잘 안 돼서 이 정도 선에서 서스펜션 시스템 마무리 짓고 넘어가기로 했습니다. 네, 맞습니다. 저희가 이제 베이직 사이테이션을 범프의 스케일, 그러니까 범프의 개수랑 이제 디멘션을 아니까 베이직 사이테이션으로 저희가 고려를 해서 그래프를 낸 다음에 결론이 제타를 증가시키기 위해서 K를 낮추고 이제 C를 좀 높이는 쪽으로 해서 P 게인을 낮추고 이제 D 게인을 좀 높여보려고 했는데 생각보다 저희 그거의 컨클루전이랑 저희가 직접 해본 이 결과랑 다르게 나와서 그 부분은 이제 이 정도 잡은 선에서 마무리 짓고 넘어갔었습니다. 근데 그 제타가 E 루트 MK분의 C라서 저희가 컨클루전이 제타를 인크리즈 한다는 쪽으로 나와서 이제 매스를 이제 올리는 쪽은 최대한 피하고 이제 K를 올리거나 K를 낮추거나 C를 올리거나를 결정을 해야 되는데 그래서 이게 벌추얼 스프링인 P 게인을 좀 낮추고 벌추얼 댐핑인 이제 D 게인을 좀 높여보려고 했었습니다. 네. 단순히 이제 제타를 인크리즈 한다는 거에서 그렇게 생각했었는데 아마 놓친 부분이 있었던 것 같습니다. 죄송합니다.
시간 관계상 저희가 더 질문을 더 힘들 것 같고요.
Okay, hope everyone can see our presentation, and we're gonna start. And this is Team E, and we are going to present our progress during a semester. And we are going to talk about, in a hardware case, mainly those three big cases. At first, in the midterm presentation, we made a conclusion that we are going to consider during those two models. And after the presentation, we got a few feedbacks from professors. The first one is that we made a wrong approach for reducing vibration. At first, we decided to match the wheel distance and the bump distance as the same and try to reduce the body's whole vibrations. But we found that this is not the best option, and we need to find a proper suspension design. And also another problem was that in the two wheels models, we use a back wheel just rotating front and back, and the professors are worried that that model can cause a problem while pivoting. So we made a few changes, and this is our final model, and those are the specifications. For the few changes, first we changed the size of the wheel. When we tried to use the given wheel from TAs, as you can see in the video, the robots are struggling in front of a bump. So we increased the size to 148 millimeters. And after we changed the wheel bigger, we can see that the robots can go over the bump. And also to reduce the weight, we use a spoke wheels, which has empty spaces on the middle of a wheel. And for the second one, we finally decided to use a four-wheel model because as you can see in the above video, when we use a two-wheeled model, the robots are powerless and is trying to slide down and fell down at the uphill. So we changed to a four-wheel and we can see that it has more power and it is more stable on the ground. And also we try to use another camera and also put a LiDAR in a higher place. For a LiDAR sensor, we try to use the ICP, which means we try to collect the data for the walls and the pillar, but we want not to detect the position of a ball, so we need to put the LiDAR higher than the ball's height. And also we use two cameras because when we try only one camera, we have difficulties for detecting a ball, especially for detecting a green ball at the goal position. So we put another camera at the higher position and use it properly. And finally, for a pusher, we change the length. We make it a little bit longer and also a little bit narrow, so we can the pusher can surround the ball exactly, and so it makes the robots to rotate easily with containing a ball. And also to prevent the bumping at the uphill, we make a little bit curvature on the pusher. For the anti-vibration, we basically use the characteristics of air suspension. The air suspension has a characteristics that we can change the spring and damper values while the vehicle is running. And to use these characteristics, based on the guideline version 2, we add another additional joint between the motor and the base link, and we try to put in the characteristics of a prismatic suspension joint. For a theoretical way, we try some progresses. First, we try to make the ground position change like this, and we try to use a Laplace transform, but finally the results were become too complex, so we were unable to use it. And another method is a simple way. We assume that the ground is like a harmonic function, and we made the equation like this. And as you can see in the equation, the resonance to reduce those values, we need to increase the value of the R. So we made a conclusion that we need to small the stiffness value, and also increasing the damping value will become the best results. And this is the data from the IMU sensor when we make the robots to overcome one bump, and by changing the parameters. And when we collect those data at one chance, at one graph, we can see that when we set the PID values such like that, this becomes this has the least maximum overshoot. So we try to use this model. We have some difficulties while working on the suspension. At first, the results become random. Even though we use the same condition, the results were changing variously. And sometimes when we change a parameter a little bit more, the robots become very unstable, and sometimes it broke down in the gazebo situation. And we guess that changing a 1 or 2 parameters only, because there are more than 3 or 4 parameters, like there's a friction parameters, damping, spring, etc. But we're trying to only change 1 or 2 parameters, and we guess that would cause a big instability. And also, so because of these results, we're trying to use chartable data based on the chartable data, and we try to use just a little bit change from the chartable data, and we get the best results.
Okay, I will explain about algorithm part first because of time. First is entrance zone, and detection part. Line is detected and position data are calculated like this picture, and these are transmitted as segments topic like this. And these are control procedure like the picture. If X position is minus, set right velocity will faster, and otherwise set left velocity faster. And also, sometimes robot can miss the line like this. Then robot continue previous action. Then robot can find the path again. Then with this algorithm, robot can pass the entrance zone. And these are bore harvesting zone algorithm. So this is overall process. And these 3 are main routine for our algorithm. And avoid actions happen with interruption. And we made algorithms for unexpected conditions. And these are modes for our algorithm. And we use mode selection strategy to handle the actions efficiently. And we also used ICP algorithm, unlike typical global positioning algorithm. We used fixed global point cloud and current point cloud to reduce the error. So let's see the details. First is approaching ball. Robot first rotates and goes straight to the ball until the distance is 1. And next is possessing ball. First case, if there is no obstacles or obstacle doesn't affect the path, robot just goes straight to the ball. But second case, if the obstacle block the path, robot makes new target points. Robot knows RB and RP and OR vectors, so robot can know the OT vector. So robot moves to the target point and then moves the ball. And this is third case. If the target point is overlaps with obstacle, in this case, robot makes new target point and moves to the target point and moves the ball. And fourth case, worst case, if 2 target point is also overlaps with obstacle, then robot moves to new target point as much as possible, then move to the goal. Next is carrying to the goal algorithm. but it is very similar with approaching ball algorithm. So, but the target is changed. It is goal area, not the blue ball. And this is avoid action. Robot rotates first, and when the robot without ball try to avoid the red ball, it revolves. But other cases, the robot goes straight. And while testing, we met so many unexpected conditions. First is when the blue ball is behind the pillar. So robot calculates the global position of map center with ICP. The robot moves to the center and detect the ball. Second is when the obstacle is in the pusher, then robot detects it and move backward to avoid them. Third is if robot gets stuck in the pillar, robot just goes straight to get out from the pillar. Fourth is when the blue ball and robot place like this, so they will rotate. For this, robot move back to solve this. And fifth is robot gets stuck because of the pusher at the goal area. For this case, robot move backward little and rotate to solve this. And final is when the goal area is not detected because of pillar. For this, we also use ICP to find the global position of goal area. So let's wrap up the algorithm part with these 3 key points. For line tracing, we use that way to make the robot move for any cases. And for ball harvesting, we use mode selection strategy for efficient action handling. And we use target point method so that robot can possess the ball for any cases. And we use the relative position method to solve the problem of ICP. And before we finish, let's see the short video. And this is easy case. And as you can see, it works well for the easy case. And this is hard case. Like I said before, we made many algorithms for unexpected conditions. So the robot can do those hard cases. Yep. Oh, so this was Timmy, and thank you for listening.
질문은 하나, 2개 정도 받으십시오. 질문하실 때 마스크를 살짝 내려주시기.
수업 편집 중에 질문을 하는데요.
네.
범위를 여러 개 만들어서 지나가고
네네.
지나갈 때 범위를 좀 지나가는 시간이 없는데 한 범위에서 다음 범위까지 지나가고
범프에서 범프로 말씀이시죠? 거의 우선 로봇 크기 전체로 보면은 범프를 거의 웬만하면은 한쪽 타이어가 올라가 있는 동안에 다른 범프 사이에 끼어 있는 게 계속 연속적으로 나타났고요. 그리고 그 시간상으로는 저희가 그 리얼타임 팩터가 조금씩 달라졌는데 저희가 이용을 할 때는 거의 한 2초에서 3초 사이에는 지나갔던 것 같습니다. 그 내추럴 프리퀀시 말씀이시죠? 저희 계산할 때 대략 28.7 몇 정도 나오게 계산할 수 있어요. 네. 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 알겠습니다. 네, 알겠습니다.
지금 꼭 하셔야겠다. 그럼 일단 시간 관계상 죄송합니다. 생각은 점심시간을 조금 늦춰야 될 것 같고요. 근데 오후 세션은 저희가 부탁드리는 것이 있어서 점심시간 정도 한 30, 40분 정도면 충분하지 않으실까 싶어서 그 부분을 양해 부탁드리고 한 12시 20분, 30분 전에는 일단 번째 팀, 다음 팀 나와서 발표 준비해주세요. 다음 팀. 준비하는 동안 하면 지금 일단 줌으로 발표하는 팀은 비슷한 세팅이 좀 힘들 것 같아서 아마 줌으로 할 팀은 유튜브 녹화 이거 보여드리기 포기하고 그냥 줌으로만 발표 일단 시켜서 마이크 직접 뽑아가지고 활용해요. 여기 있는 분들은 그냥 중간에 할 것 같아요. 마지막에 할게요. 중간에. 오셨어요? 여기 있었어요. 그러면은 여기서 갈 거예요.
Hello, everyone. This is Group G. We are starting our final presentation of Group G. First, I will present the first hard part of this presentation. My name is Jung Moon-gyu. We will cover these 4 topics. First, I will talk about concepts of our robot system. Our goal of this project is making robot simple, safe, and to complete the mission. This is hardware of our robot. For sensors, we have 1 LiDAR and 2 cameras for vision processing. Also, we have 2 wheels and 2 rear sphere caster wheel for pivot driving control. We build the software for our robot in only 2 nodes. First, the data node. Data node collect all the sensors data from camera and LiDAR and calculate some useful variables for suggesting additional information of the environment. And driving node is library of driving signal with condition statements. So after subscribing cognition data from the data node, the driving node find an appropriate driving functions and transmit to the robot as a driving signal on the motor. We compare this driving node as the encyclopedia for robot. We consider every situation by using real-time measurement from the data node and through if or else statement. If the robot needs some solution of current state, the driving node suggests the appropriate solutions like this. Now we are going to talk about hardware. These are the pictures of previous model and the final model. You can see that the overall structure of the robot hasn't changed that much. But in detail, through the several iterations from the gazebo simulation, we evaluated the suitability of each component for the robot. Weight reducing and dribble control and easy to pivot turn and vibration tuning is our main consideration of hardware design. We applied FEM analysis to check safety of entire structure of the robot and reduce the weight of the robot. This is simple FEM analysis result of the model's body regarding the given value of yield strength and Young's modulus. we conclude that our robot is safe in the gazebo environment on this structure within its expected nominal forces, exaggerating on the robot. Next is weight reduction. To reduce the weight without that, changing the bar is best option. So we found some different aluminum profiles are used in real life. We checked that all of these are safe under the force 10 kilonewton. So we can use this 22 by 22 profile, which is the lightest. In the case of wheel, we used ball wheel to make pivot turn easily. By theoretical analysis about the wheel size, because the bump is round shape, height becomes smaller than the real value, can occur the minimum torque for the breakthrough bump. As a result, we assume that wheel radius to be at least 3 centimeters. We checked that from the several experiments from the gazebo. Next part is suspension. We designed like this, and because we had to make it simple, but the overall design is coming from this suspension system, McPherson suspension system, and this is a stiffness and damping ratio calculation process. We, considering external forces, we estimated the minimum stiffness should be 500 Newton per meter. And the graph shows various damping cases, and we chose the critical damping for the best efficient damping ratio. So we simulated many cases with different C, and this video of the suspension system experiment. From the result, we conclude that the critical value C is 54 and shows the smallest vertical acceleration on the simulation. From this overall progress, finally, we made this final model.
Now I'm going to talk about our cognition method. And to start, we use 2 cameras for the line tracing and also ball detecting and checking the collector. And also we used one lidar for checking the pillars and the walls. First of all, our first goal is line tracing. So we count the number of segments of the black line, and to check whether if it is the bumper course or not. And also we divide the black line into few segments and calculate the center of the mass of each segments of black line. And using the center position, we provide the trend line and offset value and also the direction for the robot. Our second goal is ball harvesting. So in order to get more precise ball position value, so we use the calibration using least square method. So using least square method, we calculate the calibrated coefficients for optimized ball position value. So using this, we reduced our error up to 20 millimeters in gazebo map. Now we are going to look at our specific process, how it works in the ball harvesting area. So we divided we thought of whole process of ball harvesting in as we thought of this whole process as a repetition of these process. First of all, when there is a blue ball in the collector, we set the target as a green ball. If there is no blue ball in the collector, we set the target as a blue ball. So first of all, we set the target, and next we find the target, align to the target, and approach to the target, and do the final process like ball harvesting or goal in. So we do it again and again until we make all the three balls in to score in. So let's start from the basic. So we just do the just turn and just go. And using this, we can align to the green ball, align to the blue ball, and approach to the green ball and approach to the blue ball. Also, using this, we can do the harvest. We can harvest the blue ball. All of this can be done with real-time feedback functions, but only using the real-time feedback function, we cannot avoid the obstacles, and we cannot do the goal-in function, and we cannot overcome the errors. So we divide our whole process into two types. We use the real-time feedback function and also the macros. So using the macros, we overcome the problems of avoiding the obstacles and avoiding the walls and do the goal-in functions. 넘겨둬요. So to explain our first macro. The first macro is to avoid the column. So first we detect the column by comparing the injected distance value from LiDAR distance value. So if the injected value have the difference greater than 15 centimeter, we consider it as the edge of the column. So if the column is detected, we need to avoid it. Like when the column is detected, robot turns and goes straight and turn again while it aligns to the blue ball. So turning and go straighting and also turn again is a one macro. But we thought of some hard cases that when the blue ball and the column is near enough, then the robot goes behind the column and collect the blue ball vertically. Our next method. Because of time problem, I think we should skip some macros that we want to explain it. So for the end of our presentation, we're going to talk about our unique points exception handling. Due to the nature of the ROS and gazebo, so errors are sometimes difficult to predict. In almost every cases, a compensate macro is ready to overcome this. Shown on the left is a compensate macro of failing to align the blue ball due to an unexpected error, like blue ball cannot be detected well. So the robot go backward for a while and do the process again. So even if this is a right way, there could be an error. So we spent a lot of time to catch out this unexpected error. We modified our code to avoid this error, and also we made a compensate macro as introduced before. And this is all of our presentation, and thank you for listening. 네. 저희 FAM 그 담당하셨던 분이 답변 주시나요?
그 기존에서 10kN을 같은 힘으로 가정해서 측정한 건데 그 10kN을 준 이유가 저희 로봇의 질량이랑 그 시뮬레이션을 통해 측정한 가속도로 간단히 F는 A식을 이용해서 힘을 계산해 보니까 대충 600N 정도 나왔는데 다른 외부적인 충격에 의한 그런 힘도 있다고 생각해서 충분히 큰 힘이 10kN을 가져내고
이게 포맷을 서스펜션 보니까 거의 플라자 프로그램이 같은데 플라자 링크 같은 자동차 서스펜션 프로그램 하는 거 예전에 디자인 중에 서스펜션을 다양하게 만들어 보고 있거든요.
지금 뭐 다양한 케이스 보여주실 필요까지는 없고요. 네. 말로 그냥 설명해 주세요.
그럼 저희 슬라이드잖아, 슬라이드. 네, 슬라이드 자동차 서스펜션의 슬라이드를 만드셔. 링크예요.
예, 그럼 발표 이거를 마치도록 하겠습니다. Try to finish in 10 minutes, and then we'll have a couple of minutes for interaction. Yes. Do you need?
Yes. Is this something?
Because he's going to share the slide, so you don't need this laptop. It's good. You can put it down.
Can I keep it for my workshop?
Yeah.
Yes. Here's the link. Do I get the control?
No. So he'll change the
Will
slide.
be changing the slide. Thank you so much.
Yes, I'll take your finish it.
Sorry.
We have you can't control this while you take your finish it.
You should do it.
Maybe is this working?
Yeah, I'll try it. I'll see. Okay. Oh, it's working. So good morning, everyone. We are Team H under the supervision of Professor Ku, and we hope you'll enjoy our presentation. So we cover our contents in three sections. First, let's go through the. I'm sick actually. I mean, yesterday. Okay. Let's go through the. Is it better now? Let's go through the hardware design first. So we had to change the car's design in the following way. From our design review one, we made some mistakes before. So the rightmost car is the final model now, and let's look at its key features. So first, the first feature is its two-wheel actuation system. The two-wheel system helps improve the controllability as it can turn with a lower radius, and also we improve the stability by including two caster wheels in the back. Also, we did like center of mass considerations, especially over the slope that we were given, so that our car can easily overcome the slope. Also, for the ball holder, we use a magnet-shaped structure for the larger contact area with balls. So the angular wing design prevents the ball from touching wheels, and also it sweeps away any unwanted balls from the path of the vehicle. This is our suspension design. We used a double shaft suspension to prevent any torsional rotation, and also for gaining like optimal PID values, we used computational methods. So this is our screen from Simulink. We carried out tuning using MATLAB Simulink, and we assumed that the car's vibration was that of a complete base excitation model. And the Y input was the time domain for the wheel path on bump. We added center of mass considerations, and into the model we added constraints like maximum allowable acceleration and also maximum displacement that's allowable. And these are the optimized values that we got, which we added in Gazebo. And after more fine tuning, this is our result. We managed to bring it down bring down the vibration by some extent. So next is the software design. So first, to complete our task by actuating the vehicle that we just showed you, we have to process the input rate. So for entrance, the heading direction was calculated by using using LiDAR data and the black line. So after entering the ball harvesting zone, we reconstructed the total map by positioning vehicle and balls. And to separate the two modes, we used an intermediate mode transition, and I'll talk about how that works shortly. So for sensor configuration, we used three cameras and a LiDAR. The center camera, it's mostly for alignments of objects, and the left and right, it forms a stereo camera for depth and position estimation. So this is our entrance navigation. We use both the LiDAR data and camera. Initially, we use camera to look for the line, and in case when we see the slope, we just go straight without any change in direction with full speed. So in case there is like missing if we don't see the line properly, we use the LiDAR data to like find the line again. So after completing the navigation in entrance stage, we detect and transition to ball harvesting stage using these two criteria, the intermediate mode that I was talking about. It's the first criteria is that we have to detect a color of the balls, red or blue, and second is that we need to find a certain number of LiDAR data that has a distance of more than 3 meters. So only then our mode will shift to ball harvesting system. So to navigate the ball harvesting to navigate in the ball harvesting zone, we collect the PCL point clouds of the vehicle, and this is what we get, and we try to optimize we try to solve this as an optimization problem, and we minimize the area of the outer rectangle. So that gives us the orientation, and next we do wall fitting so that we can calibrate our model. And based on this orientation data and based on our results so far, it was pretty accurate. We were supposed to bring down the error by less than 5 centimeters. So localization was working well as well. Next, it's the relative distance between the car and the balls that were calculated by the principle of stereo camera and triangulation, as you can see over there. So it calculates the distance by pixel values of each ball in the image. So for detected balls, we determine the absolute position using this simple geometry. So as I said, we got the absolute orientation and position of the vehicle. We have the relative position of the ball. So we just use that to get the absolute position of the balls. And we converted this is almost like DQN. So we converted the stage area into 2D array like lattice. And when our car calculates a ball position, it increases the count in that respective array position. And also whenever our car goes over over a certain data point, we initialize the data value in our array, and our car heads to the highest ball count when it needs to go to our target ball, and yeah, so that's how we get our ball's position, get to our target ball, and as it's heading towards the ball, it gets even a more accurate ball position. So it just keeps on getting better. So for path planning, the best path is always the straight line, but it's limited in our map because we have obstacles. So obstacles like pillars. So what we did was we generated, and we declared a region of circular danger zones with those areas, as you can see, with a radius of 40 centimeters, because we took into consideration the dimension of the geometry of the pillars and also the vehicle. So and then our algorithm would calculate. It would calculate the shortest curve path using some iterative process. And the best part about this is that after calculating this iterative process, it would give the velocity orientation of the velocity vector as input, velocity reference for the motor's PID control. And the advantage of this is that it's smooth; it does not need to stop, so it won't lose the ball from the holder. And also, it's shortest. I mean, according to us, it's the shortest that we found in terms of times taken and also energy efficiency. So yes, that's that. So we use center camera, as we said, for aligning, right? So we do this for docking basically. It finds the accurate direction to get to a ball in a holder by setting the centroid of the target blue ball and the center of the camera. So even though stereo camera can get only the rough target ball position, fine docking was possible due to vision alignment process. Also, we can get the holder state, to know whether there's like a blue ball or a red ball or if it's empty. And I will explain how we use that data now. So basically, the entire process of ball harvesting uses the functions that I previously showed in the few slides back. So it first drives to docking position by path calculation from the current position. And then after vision alignment, our vehicle goes straight forward to the ball until the ball is in the holder. And then we call this as the docking process. And from docking position, we calculate the docking position to the opposite of the hole from the ball position. And so the vehicle can basically collect the ball and go straight inside the hole. So lastly, I'll talk about some of the exception handling process. Our system, first of all, if our system was not moving for more than 2.5 seconds, we consider that to be as a stuck state. And in that case, we go slowly backwards. So second case is when we go backwards, there might be some obstacle, and it started to flip. So we check for any obstacle in the back. We check for any obstacle in the back, and if they were close, we would stop. And third, if the stereo camera was not exposed for long enough, we could not detect the ball. So if it could not detect the ball, it would carry on infinite loop until it could find some blue ball in the region. Fourth, if there was any red ball in the holder, we have a mechanism where we just turn and the red ball is released. This is where we use the central camera data as well to get the holder state. And last, sometimes due to stereo camera internal errors, intrinsic errors, there is false ball detection, blue ball detection. In those cases, the robot will go to that position and check if there is a ball. If there is no ball, it will initialize the count value that we used in previously, the DQN process. So yes, these are our demo videos. This is the case for the entrance region. And finally, this is the case where it avoids obstacles and takes the ball and drops the ball towards the goal. So that was our presentation, and I'm sorry I was sick, so we had some problems in the morning. I hope you had if you have any questions, please ask. Wide what? Yes, that's why is it wide?
얇은 프레임으로 제공되었던 20mm짜리 프레임을 써서 거의 최대한 레슨이 들어가도록만 하게 한 최대한 압축한 상태. 그래서 꽤 크고요. 그리고 그 전에 이제 저희가 스테레오 카메라를 계산을 할 때 그 두 카메라 사이 간격이 필요하지 않습니까? 이 카메라의 간격 사이를 25cm 잡아둔 것도 있었기 때문에 그 두 개가 복합적으로 해서 지금 그 간격을 유지한 상태에서 최대한 압축한 상태라 상대적으로 넓긴 하지만 저희가 최적화를 하는 방법이 있고, 물론 그 디스턴스를 더 줄여서 최적화할 수 있겠지만 시간상의 이유 거기까지는 도달이 못했고요. 지금은 저렇게 디자인한 건데.
Yeah, and also I think that is one of the weaknesses of our vehicle. It's a little big, so we had to make for better, maneuvering around the obstacles. We had to make changes in our algorithm, like docking position and the radius and stuff. So that is one of the weaknesses that we also had to spend time in working on, basically in our algorithm part. Thank you so much. Sorry again.
그 사람이 네, 저기요. 지금 32분인데 40. 저기 보내지 않았어요? 제출했을 텐데. 그래 한번 체크해보세요.
이거 프레젠트 되는 건가요? 프레젠트 되는 거예요?
파일 카피 해놓지 않았나? 네, 줌으로 공유해줘요. 화면 공유.
네, 시작하도록 하겠습니다. Hello, this is Team B. Let me present our vehicle design progress for our mission. We distribute our role as shown here, and we divided our presentation into 3 parts. First, system overview, and second, hardware design, and third, software design. We'll start from showing the main concept of our design for the mission. Then we'll elaborate on the details, first on the hardware design, and then software parts. Our mission has 2 parts: getting through the entrance zone, followed by the ball harvesting zone. For both parts, we need to ensure energy efficiency and reduce the required time to finish the mission. Also, especially for the entrance zone, we must deal with the vibration. The most significant feature of our design is the pivot turn, which is to rotate itself in place as shown in the video. Pivot turn enables nimble and efficient steering and prevents losing the ball while having the ball, and simplifies the ball harvesting algorithm. Please watch these 2 short clips. As you can see, the paths become much simpler when the vehicle can do pivot turn while it has the ball in the basket. This is our final design of our vehicle: 2 driving wheels to the front and 1 caster wheel to the rear. When the vehicle has the ball in the basket, the center of ball is right between the center of two front wheels. This makes the ball remains inside the basket during the pivot turn. Before we designed the vibration compensation system, we simulated linear system which considers bump shape and hill size. There is optimal K and C because there is a trade-off between low acceleration and vibration suppression. Also, large radius of wheel produce low vertical acceleration of the vehicle when it drives over the bump. So we set the radius of the wheel to the maximum value allowed in the guideline. We calculate the shootable acceleration region for our vehicle. The shootable acceleration is when the normal force on the front wheel and the rear wheel not zero, so that the wheel can translate the friction force to the axis without issue. When the vehicle accelerates, it should have an acceleration under 15 meter per second scale and under 5 meter per second scale when decelerating. When the vehicle climbs forward, the acceleration should be under about 5.8 meter per second scale and less than 1 meter per second scale for backward climbing. We also check it that it does not roll over during rotation or cornering. The graph shows safe range of cornering radius for each vehicle speed. Pivot turn is the case of zero vehicle speed, which basically means that the vehicle will never roll over during pivot turn. Now I am going to explain the software that controls the hardware part of our vehicle. There are two separate parts in our design. One is the control vehicle in entrance zone, and the other is conduct for harvesting. Let me introduce you the entrance zone strategy first. Our original plan to get through the entrance zone was the following line, but we realized that this method is extremely unreliable when the vehicle is on the bump, since the vehicle continues pitching up and down. Instead, we made the world detecting node which controls the vehicle using LiDAR information. There was an issue that our front wheel drive design was not suitable for climbing the slope due to its rather extreme inclined angle. As the solution, we had the vehicle to climb the slope backward. By doing so, the vehicle can climb the slope with the friction coefficient less than unity. As the result, the vehicle can pass through the bumps and the slope as well. We observed that the bumps helps the vehicle to align itself as long as the vehicle is roughly aligned with the bump. A vehicle climbs the slope backward. Now for the ball harvesting part, we have 5 nodes that communicate with each other to complete the mission. This diagram shows ROS communication between 5 nodes in our system. First, ball detection node calculates and publishes position of balls obtained from the image data. And vehicle positioning node conducts odometry using LiDAR scan topic. Mission control nodes actually sends an order to the pathfinding node to find the route of the vehicle according to the progress state of ball harvesting. Then vehicle control moves the vehicle based on this route proved by the pathfinding node. I will explain each node in detail in the following slides. In ball detection node, we use both the RGB camera data and depth camera data to utilize in find ball. RGB image is used to find the rough location of the balls of each color on the image using half circle detection method. The depth camera finds the point of minimum distance on the circles detected on the RGB image. It uses the projection matrix to find the relative coordinate of the balls. Then it calculates and publishes the absolute coordinate of the ball using the beaker position data obtained by the beaker positioning node, which I will introduce on the next slide. The beaker positioning node uses the ball information obtained by LiDAR. After some image processing, it obtains the angle and distance of the balls. The location and the orientation of the beaker is calculated from the balls data with error less than 1 centimeter and 1 degree respectively. When the entrance control node notifies that the beaker passed through the entrance zone, the mission control node to control the whole ball harvesting process initiates. The mission control node starts with detecting the balls and making a list of them. When the list is sufficiently full, the node gives an order to the path finding node to make a proper path. That leads the beaker to the destination, which could be either a blue ball or the goal. It also gives the information of the obstacle to be avoided on the way. From the message given by a mission control, path finding node generate optimal paths to avoid any collision and to reduce ball harvesting time. The optimal path is generated as an array of checkpoints using A-star algorithm, which is fast, accurate, and intuitive. Finally, the beaker control node uses checkpoints subscribed from the path planning node, pivot turning on each checkpoint and driving straight to the next checkpoint as the routine repeated until the beaker arrives to the destination. Although I have explained you about the various features in our beaker so far, I'm really sorry to inform you that our beaker still needs some adjustment even at this point. We confirmed multiple times that the beaker can pass through the entrance zone, but we were not able to complete the ball harvesting part of our system in time. With this status quo, which was rather painful to report, I would have to end my presentation. Thank you for listening. 어떤 부분이요? 네. 그 보드 경사지게 달아놓은 이유요. 이제 비크를 컴팩트하게 만들어서 이제 피벗 턴을 할 때 그 전체적인 회전 반경을 줄여서 그 다른 옵스테클에 부딪히지 않도록 하기 위함이었습니다. 왜냐면은 이제 거기 들어가는 보드가 상당히 길기 때문에 이걸 기울여서 달면은 줄일 수 있잖아요. 그래서 네, 회전 반경을 줄이기 위해서 그렇게 설치를 했습니다. 회전 반경 자체는 크게 줄어들었지만 저희가 볼 하베스팅 그 존에서 하는 미션들을 전체적으로 수행하는 걸 완성하지 못했기 때문에 이게 얼마나 효과 있었는지는 이제 말씀을 드리기가 조금 어렵습니다.
말씀 다 하셨나요? 다시.
어떻게 구현하는 것도 고려해봤어요?
실제로 구현하는 것도 이제 가제부상에서 그거를 트랜스미션을 넣어서 해야 되는데 가제부상에서 에러가 자꾸 생겨가지고
가제부 가기 전에 서스펜션이나 뭐 링크가 있다든가 뭔가 슬라이드 같은 거 뭔가 있어야 될 거 아니에요? 아직 그 부분은 안 했나요?
그 서스펜션의 그 조인트를 만들고 거기에 트랜스미션을 넣어서 이걸 제어를 해야 하는데 가제부상에서 작동을 시키려면 그거 하는 과정에서 이제 에러가 자꾸 생겨가지고 충분히 그 부분에 대해서는 구현을 못한 상황입니다.
알겠습니다.
그 발표 그 중에 그
네.
뎁스 카메라라는 표현이 있었는데 정확하게 어떤 센서들을 어떻게 사용을 한 건가요?
저희 파일 URDF 상에서 보시면은 저희가 사용하는 카메라가 이제 생긴 거는 로지텍 C920이라는 모델처럼 생겼는데 실제로 URDF 상에서 디스크립션을 보면은 인텔 리얼센스의 그 플러그인을 사용하게 되어 있어요. 그래서 실제로 퍼블리시하는 데이터가 RGB 데이터랑 뎁스 카메라 데이터 둘 다 나오게 돼 있어서 저희는 거기서 뎁스 카메라 데이터를 사용을 했습니다. 그러니까 카메라가 이제 전방을 볼 때 그 카메라부터 떨어진 거리가 나와요. 픽셀마다.
그럼 다음 팀 발표 넘어가겠습니다. 실자 이쪽으로 오시고요. 마이크에 담고 지금 45분이니까 10분 안에 55분까지.
Good morning. I am Bak Bin Hyuk, presenter from Team C, and our professor is Professor Choi Se-bom. Now I will be introducing our car robot Total. Meaning of our car Total is collection of things we learned in ME department. This is the video of car Total operating in simulation program Gazebo. I will be introducing the algorithm part first, from entrance zone to ball harvesting zone, and the hardware next. SLAM is short. This is ball harvesting zone. SLAM is the short form of simultaneously localization and mapping, which accepts LiDAR data process to process mapping. But we had problem that red ball is not recognized as obstacle. So we had converted our camera data of red ball data to added into SLAM algorithm to make our car recognize as red ball as an obstacle, which is shown at the right image as red dots. Next slide is about detecting the balls and converting them into axis data. Car gets original image from camera and use enrich function to separate balls by their color and sharpen the image by threshold. Next, every ball image pixels are replaced by distance background pixel by distance transform function. If two balls are overlapped, they are separated by threshold value and get separated area, and after this process, each area is filled with different color. Until the original ball boundary. This result is then used to make contour and find the coordinates of the ball. This way, we can find the ball that are overlapped or hidden behind the pillar. In the previous slide, we had found the red balls data using few functions and algorithms. And this slide, we will show how those data are used for mapping. First, we get data from camera. We accept relative position from camera, but using the location of car and relative position of the ball, we can get absolute coordinates of the ball. And next, the car will label the new absolute position of the ball by comparing previous absolute position. And when comparing the data, the least error will be considered the same ball and labeled as same ball. When we get two data of the same ball, one that is new and one that is previously observed, the data that is collected at shorter distance has higher priority and updated. And this data is given to LiDAR for SLAM. This is our mapping by SLAM, and using the mapping, here we can see the pillar and red ball shown at the map. These objects are considered as obstacle, and car will be planning the shortest paths to the goal. Next slide is about how paths is planned in the car. There are three regions: occupied, free space, unknown. And by using the explore algorithm, car will be planning paths avoiding the obstacles and pick up blue ball that is located in unknown region. In this process, new obstacles and new free spaces will be updated real time. So while moving, car can update the map and plan the new path simultaneously. Coast map is about how actually the path is planned. As shown in the name, regions of the maps are divided into coast to visit the region. Cost of regions here is determined by three elements: distance from car, distance from goal, presence of obstacle. And those three elements are used for different ways to calculate cost value, and using values of cost, lowest cost paths is finally selected for journey of our car. Next is entrance zone. Here we get the low image from camera that is taken, and using those image, threshold value is used to process the image and to white and black. The image is divided into 5 regions. These 5 regions will be the key to determine the direction of the car. When there's black pixel in the red region, over the threshold value, car will move to that direction. If not, the remaining will be considered, and region that has the most black pixel is selected for the region, for the direction. For our suspension, we had few worries about entrance zone. If frequency of repeated force is equal to natural frequency of the car, there will be resonance. So we had to calculate the suspension value to reduce the effect of forced frequency and the resonance. But the scene here, value of K came out too small that our suspension is, if our suspension car is placed on the suspension, deflection of the spring will be too large. So we came out on new idea that our maximum allowance for deflection of suspension is 0.03 meters. And we can calculate spring constant from this allowance. By this method, we got 327 Newton per meter. From this value, we found the value that is given minimum acceleration of the car using trial and error method. This is our test of suspension system to determine the value of K and function of suspension. However, we tested the effects of suspension by comparing data of no suspension, prismatic suspension, and revolutive suspension. But as seen in the graph, there was almost no effect of suspension on the maximum linear acceleration of IMU. Next is hardware design. Our initial model was 4-wheel skidding car, but since there was problem with skidding, we had come to idea of 4-wheel and 2-wheel two-caster and 3 wheels. And our final model is 3 wheels. This is 4-wheels car, and we had few problems with 4-wheel car. If we make front wheels rotate at the same amount, there will be skid steering. Our center of turning is different for each wheel. And one more thing, that this model cannot rotate in place. But if we implement separate steering motor for each wheel, we can make the car turn and rotate, but we need too much motors. Now we will be looking at two wheels and two caster model. This model can rotate in place, but there are critical disadvantages that suspension cannot work efficiently. As there is no horizontal friction force from the ground to wheel, there will be no horizontal force transfer from suspension to body, meaning we cannot reduce pitching motion of the car. Now this is our final model, three-wheel system. Advantage of this system is that car can rotate without going forward and turn without skidding. We have also implemented our suspension system to reduce rolling and pitching motion. We have aligned our suspension joint, ground contact point, and center of mass in a line to match our rolling and pitching center to the center of mass. In this way, we can minimize rolling and pitching effect. This is our final type of car with few mechanical features in it. We had improved our model by trial and error with engineering calculations. There is one steering motor with one driving motor at back wheel, as introduced earlier. COM at low height for stability. Large wheels with wheel guard for preventing collision. And there are two cameras for one line tracing and for one ball harvesting. Lastly, we have aligned suspension link horizontally so that wheels maintain vertical alignment while suspension is working. Thank you. Any questions?
제일 많네요.
예.
세 개요. 그게 그 피벗턴 아까 이렇게 뒷바퀴 패러렐하게 나가지고
네네.
옆으로 나가지고 피벗턴
네.
그게 할 때 앞바퀴 두 개 스키딩 될 텐데요. 불안해지지 않나요? 시뮬레이션이?
스키딩이 안 되게, 그러니까 센터 오브 베스가 결국에는 보시면은 뒤쪽으로, 그러니까 여기쯤에 생기거든요. 그러니까 센터 이거 하나를 앞으로 가고 하나를 뒤로 가고, 그리고 이거를 옆으로 돌리면은 그 센터가 결국에는 중앙에 생기잖아요.
예. 그러니까 계산적으로는 이제 이거나 다 되는데요.
네.
그러니까 우리가 이제 계속 학생들이 리포트했던 문제점 중에 하나가 바퀴가 스키딩 되면은 전체적으로 시뮬레이션이 불안정해진다였는데요. 저게
근데 저희가 지금 이거를 실제로 로테이트 해봤을 때는 문제가 생기지 않아가지고 스키딩이 안 생기는 걸로 저희는 간주를 했었습니다.
알겠습니다.
그래서 타임 스텝마다 미팅하는 앵글을 조금씩 줄였어요. 만약에 지금 상황에서 앵글이 30도 정도 되어 있는데 여기서 0도로 바로 바꿔버리면 슬립이 일어나면서 컨트롤을 제대로 할 수가 없었는데 타임 스텝을 여러 구간으로 쪼개면서 5도씩 이렇게 오전 나가는 방식으로 최대한 슬립을
예, 알겠습니다.
피칭을 잡을 수 있다고 얘기를 했는데 어떻게 설계를 해서 피칭 모드를 잡을 수 있게 서스펜션을 설계를 했는지 좀 설명해 주시겠어요?
저희가 뒷바퀴가 보시면은 얼라인이 결국에는 센터 오브 매스 쪽에 되어 있거든요. 저희가 애초에 원래 실제 차에는 두 개의 서스펜션 링크가 들어가서 결국엔 롤링 센터랑 피칭 센터가 생기잖아요. 근데 저희가 하나밖에 없어가지고 롤링 센터나 피칭 센터를 찾는 거는 쉬웠어요. 그래서 그거를 얼라인을 해가지고 결국에는 서스펜션 링크 쪽을 설계를 하였습니다. 혹시 다른 거를
액추에이터의 방향을 바꿨다는 얘기예요?
그러니까 서스펜션 쪽은 결국엔 가만히 있고요. 여기 위에 보시면은 스티어링 모터가 따로 있는데
그러니까 지금 서스펜션이 어디 있습니까? 스프링하고 댐퍼가 어느 방향으로 있는 거예요?
저희가
잠시만요. 저희가 과제보상에서 이거를 구현을 하기 위해서 하기 위해서 조금 다른 방식을 과제보만의 그 레볼루트라는 지금 바디하고 그 서스펜션 링크 그 사이에 그 점에다가 레볼루트라는 포인트를 넣을 수 있는데 그러면 이제 그게 이렇게 회전을 할 수가 있습니다. 그래서 그 포지션에다가 P값 값을 넣어서 그게 사실 고정을 해주는 게 사실 현실하고는 좀 다를 수 있어도 서스펜션 효과를 한다고 저희는 생각을 해서 그래서 뒷바퀴는 이제 레볼루트로 해서
그 레볼루트 포인트가 어디예요? 레볼루트 조인트가 어디 있어요? 위치가? 아까 그림에서 좀 보여주세요. 어딘지. 저기서 어디를 얘기하는 거예요? 서스펜션 조인트라고 부르는 부분에
점입니다.
녹색 점?
네, 녹색 점이요.
녹색 점이 레볼루트 조인트고 거기에 앵귤러 스티프니스와 앵귤러
네,
댐핑을
그렇습니다.
집어넣었다? 이렇게 이해하면 되는 겁니까?
예, 그렇습니다.
근데 지금 미케니즘이 어떻게 직선으로 연결이 돼 있어요? 그 뒷바퀴가 그럼 그 조인트로 보여야 되는데 조인트로 안 보이잖아요.
예?
조인트로 연결이 안 돼 있잖아요. 지금 하드웨어는.
아, 지금 휠가드 때문에 안 보이는 거지. 그러니까 이 휠가드를 들쳐내면은 안에 쪽에 연결이 되어 있습니다.
그러니까 그 휠가드 없애고 나서 어떻게 연결이 되어 있는지가 지금 안 보이거든요. 연결되어 있는 건 저쪽에 이 프레임으로 연결되어 있는 것처럼 보이는데 뒷바퀴가 그게 아니고 레볼루트 조인트에 붙어 있는 빔 형태로 연결됐다는 의미인데, 그죠? 그 레볼루트 조인트면 이게
네.
옆으로도 갈 수 있잖아요.
그게 한 방향으로만 로테이트가 할 수 있는 레볼루트라서 애초에 가제보에서
그런 걸 레볼루트 조인트라고 안 부르죠. 그런 건 레볼루트 조인트라고 안 부른다고.
저희가 그 가제보에서 설정을 할 때는 그거를 레볼루트로 하면은 한 방향으로밖에 안 움직이는 걸로 확인을 하였습니다, 저희가. 그래서 지금 보시면은 뒷바퀴가 이게 한 방향으로밖에 안 움직이거든요. 이게 숙여져 있는 것도 그렇고 다시 올라오는 것도 그렇고 한 방향으로만 이게 로테이트가 되게 되어 있습니다.
그 최종 리포트에는 그 부분에 대해서 좀 자세히 내용을 감사합니다. 예, 수고하셨습니다. 끝나갈 때 좀 일이 나와서 준비해가지고 들어가시고요. 네. 지금 2팀 남았죠? 네. 식사는 한 12시 반쯤 하신다고 생각하시고요. 오후 세션을 한 10분 정도 늦게 시작하면 될 것 같습니다.
지금 12시 10분. 네, 그렇습니다.
2분 전에.
네. We'll start our presentation. We are 공시구, 공을 보는 9명의 사람들. And yeah, this is our members. We tried both mechanical and software approach to solve the given task. So this is our strategy. We go through the entrance zone by line tracing. And then after we arrive in the point, we shoot the lidar to get initial position. And then we rotate to get the balls and pillars data. And then we draw a B-spline curve setting blue balls as waypoints. As we reach the goal point, we turn and vibrate to put the ball in every balls we collected. Let me just briefly show you again. So we will turn and vibrate over here. So these are the sub-problems we met during we solve the task. The upper three are the hardware design parts, and the lower three are software design parts. In this presentation, I will introduce these topics in a task-based approach, not a team-based approach. So our contents are like this. So right now, I'll talk about the entrance zone. The entrance zone is divided into two parts: line tracing and slope and bumps. Slope and bumps is more a design part. So hardware design is more focused in this part. First of all, the line tracing. We use Hooflines P algorithm to obtain pixel value of the border and calculate it as a vector form. We give the gain values from the distance from the center, and then our vehicle drives following the line. And also we design wheels meeting the specifications of MX28, which is our actuator. And then there were a lot of constraints or trade-offs we had to think about. The most important one is the radius and force and velocity. So we chose this one. And then by using these constraints, our final model is this. So we have 2 main wheels and 2 caster wheels. And our final model shows what will be presented. So we have a realistical prismatic joint working as a suspension. And we have 2 main wheels, as I told you before. And in the highest point, there's a lidar and a camera to detect the balls and obstacles with efficiency. And in order to cancel out the mass disturbance, we put the battery in the backside and the heavy processors under the vehicle. As you can see in the diagram and the previous model picture, our mass is supported by 4 suspensions, and the desired height change of the vehicle is 0.01 meters every time it goes through the bumper. So the suspension raw input was got from Gazebo, and also we double checked it from the SolidWorks simulation. So this is the input. The y-axis is the axis movement in scales of meters, and the x-axis is a time factor. Not the time factor, it's time. So we use these constraints to calculate KP and KD in MATLAB. We had a few iterations and a few testings, and we concluded that KP should be bigger than 160. In same method, we iteratively chose that KD should be bigger than 26. So we set the value as KP as 160 and KD is 26. The last part of slope and bumps, the center tuning. We thought the COM should be placed as low as possible between the wheels and slightly front to avoid falling while climbing the slope. And then the reason why I wanted to depict why we chose the upper part of the lidar, upper part to set as a lidar and a camera. And that's because if the camera is high enough, we can detect the balls without any disturbance. The pusher design has to be considered both an entrance and harvesting zone. Since we designed our original model to carry 3 balls at one time, it had a critical problem while going through the bump region. So we improved the design like this. The newer version is lighter and more compact, but still has the same function. I'll show you later, but it works perfectly in the goal point once it's aligned, like this. Okay, this explanation in ball harvesting zone is the key of our model. It is the most important part in this presentation, so please focus. I already talked about the pusher design, so I'll talk about localization right now. Localization starts with getting the vehicle's initial position. By using lidar data, we calculate the absolute coordinate xy of the vehicle, so vx and vy, and then the yaw value. After getting these, we also localize the obstacles and targets. We use rotation technique over here. The reason why we use rotation is that the camera's rear end screen is kind of distorted. As you see in the right hand side of the picture, the ball is squished a little bit. So we align the camera center to the obstacle so we can get the distance data without any errors. So the vehicle rotates like this and then get distance of the balls during rotation. It sends the data to coordinate data, which labels ball data and compiles all obstacle data and vehicle localization and send it to path plan node. In path planning, we use B-spline curves. Since geometrically shortest path is not the most time efficient and energy efficient path, we use B-spline. And by using this, we don't have to necessarily change any speed during moving and also maintain momentum, which leads to high energy efficiency and less time. So this is the path planning equation. It's a clamped case spline curve of B-spline curve, which we use quadratic ones, cubic ones, and then over here, we get the B matrix by inversing this equation over here. So S points depict the waypoints we go through, and the B points are the control points of the B-spline curve. This diagram shows the ith spline curve, which connects the ith ball and the ith blue ball. So this is a whole curve. And as k goes through 0 to 1, it draws a line like this. So this is defined in fxk and fyk. So rotating the rotational vector applied to heading direction plus minus 90 degrees, we can get two offset paths. So the upper path of the yellow one is for the left wheel, and the lower one of the yellow trajectory is for the right wheel. After differentiating this, we could get the velocity of the wheels respectively, and then apply them to do a very precise control. This is the path, and the way about the making waypoints, it's in the appendix. So this is how we designed the algorithm with iteration. We changed every model, added some constraints, and updated model geometries, and get the path, desired path, collecting all three balls over here. So most of them, the green dots depicts the blue balls right now. And right here, this is why we use clamped B-spline curve. So we can go perpendicularly into the goal zone and then do the vibration motion. So please focus on the path planning. We get the balls, then slowly go to the goal point. And I wanted to emphasize the vibration motion again over here. As you can see, we collect the balls. And then go to the goal point and then put the balls inside here. So sum up, our strength points is that our vehicle follows a predetermined path, which is really fast and accurate, and it's precise to control the path. And also we have a high creativity because we use the B-spline curve. It is highly used in image transforms and image animations. And also our unique pusher design is awesome. And we also have a robust design in suspension and structure, and also the centroid tuning. And these are the possible improvements we could do. So we can lower the errors and do real-time updates, position updates, and so on. Feel free to ask any questions, and thank you for listening. 그 모델 얻은 데이터는 가제보상에서 모델이 굉장히 가벼웠을 때 얻은 데이터입니다. 그래서 모델이 점점 무거워짐에 따라서 속도가 그리고 마찰력을 지금 1로 조절을 했어야 됐었거든요. 가제보상에서. 그렇게 됨으로써 모델이 범프를 지나가는 시간은 굉장히 늘어났어요.
그래서 바로 그 질문인데 똑같은 버프인데 지나가는 속도가 느리면은 땅에서 들어오는 주파수가 떨어질 거 아니에요, 그죠? 네. 그럼 그 주파수에 맞게 그 완충을 하도록 설계를 해야 되는데 좀 해석이 의미가 없어요, 이렇게 되면. 그죠?
저희가 모델을 할 때 저희가 모델이 될 수 있는 최대 속도로 일단은 맞추고 그거보다 낮을 경우에는 오토마이제이션 하나 이런 식으로 해서 조절해서 저희 최대 속도를
그러니까 열심히 한 것 같은데 의미가 없다니까 아직 지금 한 게. 알겠습니다.
코멘트 있으실까요?
예, 앞에다가 공을 3개를 모을지는 도저히 생각을 못했는데 정말 좋은 아이디어 같습니다. 저게 아까 흔들면서 3개를 집어넣는 걸 보여줬는데요. 그게 늘 성공하나요? 아니면 약간 뭔가 안 될 때도 있나요?
그 부분에 대해서 어펜딕스에서 좀 얘기를 드리고 싶었는데요. 제가 잠깐 컴퓨터를
패스트라이딩을 할때 이런 식 여러 가지 조건들을 줘서 패스가 오브젝트를 지나가면 눌러서 간다든지 이런 식으로 여러 가지 조건들을 만들어서 저희가 패스를 만드는데요. 이때 패스가 잘 만들어지면 공을 잡아서 가는데 어떤 경우에는
바퀴 마찰 때문에 스키드가 일어난다던가 아니면 어떤 경우에는 바퀴가 너무 패스가 이렇게 굴곡져가지고 바퀴를 뒤로 조절해야 되는 경우가 있었어요. 그래서 그걸 저희가 보정을 했음에도 불구하고 140도만큼 예를 들어서 140도만큼 돌아야 되는 상황에 90도밖에 안 도는 상황, 그런 상황이 가끔씩 발생하더라고요. 그래서 항상은 불가능하지만 그래도 대부분은 가능합니다.
그 골에 넣을 때요, 마지막에
네.
녹색 공 아래에 넣을 때는 그 넣는 방식이요.
네.
흔들면서 이렇게 집어넣잖아요. 저게 항상 성공하나요?
녹색 볼로 온라인이 잘 될 경우에 항상 성공합니다.
예.
저희가 좌우로 30도를 흔들게 이제 디자인을 했는데요. 30도를 해서 저희 완벽한 기체로 기체가 있다가 탑 거기에 이제 원천의 상태로 멈추는 거라고 이 부분을 아마 수정을 해야.
예. 하여튼 좋은 아이디어 같습니다.
감사합니다.
마지막 팀이죠.
네, 알겠습니다.
Hello, this is Team A. Team name is Wall A. And in first part, I'll talk about model design. This is our first model in design review 1. To make the robot rotate with the ball, we made the robot with a protruding front part. However, our first model had an increased probability of impacting on walls or columns during ball harvesting. So we had to come up with an alternative model with reduced risk of collision. This is our final model. The ball collection part is inside the body, so the model is less likely to interfere with obstacles. We also tried a model with 3 wheels and 2 motors. Although it had an advantage of smoother rotation, but it can't climb up the slope due to lack of power and the restriction on wheel friction coefficient. Therefore, we adjusted the position of component to locate the center of mass more forward in our final model. And with the addition of 2 more motors, our robot can climb up the slope without any problems. And another improvement is the number of cameras. For ball harvesting, our first primary camera faces forward, but it makes line tracing difficult. So we added a secondary camera to ensure accurate line tracing. And this camera also determines the color of the ball the robot is currently carrying. To control our robot in gazebo environment, we must find the ratio of speed and angular displacement between the actual value and the ROS input. Actual speed and ROS input have a linear relationship. However, in angular displacement case, the relationship between actual value and ROS input is not a linear relationship. So we check each input case in ROS simulation. To design suspension system, we derive equation of motion from half-car model. There are two variables, vertical displacement x and angular displacement theta. And there are two inputs, front field and rear field displacement y1 and y2. We then constructed state space model to solve these differential equations. Based on field motion, we modeled base excitation input signal for state space system. The signal is approximated to periodic half-sine signal. We consider factors such as velocity and field size and bumper distance. And rear field signal is delayed due to the distance between front field and rear field. This is the optimization process for minimal acceleration to get suspension parameters C1, K1, and C2, K2. We used MATLAB optimization application fmin_con to minimize acceleration, and the major constraint was the static deflection. First, we optimized the quarter-car model, the single degree of freedom system. Then we choose this CK value for initial point to optimize half-car model, multi-degree of freedom system. Then we simulated with our model in gazebo environment with these values and compared with IMU acceleration result. Then we adjusted the static deflection condition. By repeating this process, we found the optimal suspension parameters.
Okay, now I'll explain our team's entrance driving algorithm. Previously, we divided the webcam image into 5 sections, and the robot has a certain movement for each section. But there was few problems, including OpenCV image recognition or robot controlling problems, and also because we designated a certain movement to each section, the control was done in a discrete manner, and the robot trajectory was not smooth. To solve this, we received x coordinates of the detection box and calculated the relative distance between the midpoint of the image and the detection box. Then we published speed so that the robot can turn according to the relative distance. This allows the robot to follow the line more smoothly. The linear speed and turn factor was set as 0.6, which is most proper in several simulations. In ball harvesting zone, to detect balls, we use OpenCV functions with front camera. Most of algorithms came from base code. We just added operation of finding green ball and changed publishing message as our needs. But we faced a problem that find contours function gives us 2 contours by 1 ball. So we added another code that recognize only 1 contour by 1 ball with higher latch value. Our team originally thought that using the actual robot's location would be more effective. So we tried various ways to obtain the actual position. First, we tried numerical integration of IMU data, showed that only the turned angle data was reliable enough. And other ICP algorithm, hop transform or for location were unable to track the robot's position accurately at every moment. Due to those problems, we decided not to use the actual position and only use sensor information. This is overall outline of our current ball harvesting algorithm. The transform from line tracing mode to ball harvesting is done when the robot finds a ball with its webcam. After a ball is found, the control mode is switched to ball harvesting mode, and which consists of for large tasks. The robot searches for the nearest blue ball, capturing the targeted blue ball while avoiding all obstacles, and also finds the goalpost, then moves to the goalpost. The completion of each task is checked at every time interval, so that if one task fails, the blue ball search task will start again. Now I'll explain each task in detail. The first task is named blue ball search task. This task is completed when a blue ball is found. It has two modes: right after entering the blue ball zone and after scoring in the goal area. The robot turns around until it finds a blue ball. If the robot couldn't find a new ball, it repeats the search motion in a new location. The second task is capturing the targeted blue ball and consists of three large steps. The robot line with the targeted blue ball and approach it avoiding the obstacles. The blue ball is not detected in the upper webcam when the robot is too close to it, so the robot checks for alignment when the blue ball is close enough, then just moves forward. The lower webcam checks if the targeted blue ball is actually caught, but the webcam was too close to the ball, so a shadow was cast in the image. So we checked 9 points in the image on the webcam, so that the robot could know that a blue ball was caught. The program has an obstacle avoid queue that saves the movements needed for avoidance. The robot will align with the target, and the obstacle avoid planner will determine if avoid mechanisms are needed. The avoiding commands are saved in the queue and executed. There were some problems of the robot aligning continuously. To solve this, we increased the angle threshold for alignment, found appropriate angular speed for the robot to stop at the right angle more easily and wait until the robot deaccelerations. Task 3 is searching for the green ball while holding the blue ball. Simply, the robot will turn around until a green ball is found. Last task is blue ball return task and back off, which is moving the ball to the goal area's core and turn around to look for another ball. Because of friction between ball and robot, sometimes the ball doesn't fall out. So we tried to fix this by publishing high velocity and stopping in front of the goal area. After the robot scored, the robot go back and turn around to look for another ball. Okay, this is end of our presentation. Thank you for listening and feel free to ask any questions.
예, 수고했습니다. 그 공 캐칭하는 부분을 데모로 보여줄 건 없어요? 동영상이나 이런 걸로? 볼 하베스팅 존에서.
저희가 영상은 따로 준비는 못했고요. 그 데몬스트레이션 때.
성공을 못해서 없는 거예요. 했는데 뭐.
저희가 그 내용이 너무 많아가지고 시간 부족할 것 같아서.
결과를 보시죠. 예, 그럼 이거로 일단 오늘 발표를 마치도록 하겠습니다.
감사합니다.
Okay, this is the end of the morning session. Sorry for the delay. So we didn't have a smooth progress. Sorry about that, because we've never done this kind of thing before. So we are going to have a lunch session, short lunch break. Now it's at 12:30. So we will start the afternoon session from 1:15, after 1. So please come back to this place by 1:15. Then we will start the afternoon session. So we are going to show the demo videos what you guys did over the last semester. And 교수님들은 저희 공대 대회의실 가시면 도시락이 준비되어 있습니다. 예, 그래서 2층 공대 대회의실 가셔서 식사해 주시고 1시 15분까지 돌아와 주시면 감사하겠습니다. Okay, thank you for attendance and see you in 45 minutes.